In this webinar, we will have a closer look at some of the trace features that UDE provides. And these trace features may help you to investigate the runtime behavior of your application, for example, to identify timing issues or bottlenecks. So this is the agenda for today. In the next few minutes, I'd like to start with a briefly summarizing what we understand when we talk about trace-based debugging and trace-based runtime analysis. Then I introduce the core graph analysis as a tool included in UDE that helps you to collect profiling information and helps you to identify the biggest timing killers. And finally, I will show you how to use the core graph analysis in UDE using an example, which I have borrowed from a customer support case. So now let's get started with a few words about tracing. So in general, trace is a very useful method to get a deep insight into the runtime behavior of your application. You can basically observe the execution of your code, of the functions in your application, of tasks if you have an operating system, and also of data transfers over the buses. Trace is a hardware feature that needs, of course, a hardware unit implemented in your used microcontroller or embedded system. And the debug tool like the UDE is utilizing these hardware features. One of the key features of tracing is that you can do the observation of the runtime behavior of your system completely non-intrusive. That means that you have no influence on the runtime behavior. Your timing is not changed during debugging, and you don't need to interrupt your target system or your application while debugging. This is a major difference to the traditional run mode debugging with breaking, single stepping, and so on. Typically with trace, you can run your target at full speed, maximum clock frequency that you want to use in your application. And you can measure the timings of your application, of functions, of the execution of code very accurately. And that is obvious with that it is crucial if you want to investigate timing bugs and timing issues that you have a very exact time measurement. To make use of the trace functions, you need, of course, a target device with on-chip trace. I have said this before. There are a lot of devices on the market which provide this option. For example, the Oryx emulation devices from Infineon, or most of the ARM Cortex-based devices that implement the core side debug and trace system with the ETM, for example, the embedded trace macro cell, and also for the devices based on power architecture from ST or from NXP. There are implementations of the Nexus Class 3 standard, which provides provides tracing for code and also for data. From the tool side, you will need the debug tool, the UDE, together with an additional add-in license for the specific trace system that your target system provides, and also a UAD, the Universal Access Device from our Access Device family that provides support for the specific trace hardware. So which device from our access device family you can use depends on the on-chip trace capabilities of your target system. If there is an on-chip trace memory on the target device available, then you can even use the smallest device in our access device family, the UAD2 Pro. For targets without an on-chip trace memory, you will need an external trace memory and a dedicated trace interface to get the trace data off chip. So the UAD2 Next and the UAD3 Plus are the devices of your choice. Both of those devices support dedicated trace interfaces, either using a plug-in module shown here on this little picture, or a trace pod shown here for the UAD3 Plus. The module and the trace pod is specific to the particular trace interface your target system provides. In the UAD3 Plus, we have up to 4, in the near future up to 8 GB trace memory available and in the UAD2 Next, 512 MB trace memory is available. In general, from the debugging perspective or from the user perspective, we know two types of or two use cases for trace. The first one is trace-based debugging, and the second one is trace-based measurement. Trace-based debugging is basically useful if you try to find bugs that are, for example, caused by parallel execution or by timing problems. If you have, for example, a multi-core system. In general, this applies whenever the debugger or a debugger access to the target system would possibly hide these bugs. So single stepping and breaking a target system to find a timing issue is not a good idea, or it is basically not possible. You can use the trace-based debugging if you have to avoid any influence on the runtime behavior caused by the debug tool. Another use case is whenever you need more than a snapshot of your target state, for example, at a breakpoint. So if you basically want to look back in time, then also trace-based debugging is the right solution for that. For trace-based measurement, the trace-based measurement covers a lot of useful things that helps you to analyze the runtime behavior of your system or your application. That are profiling, call graph analysis, and also visualization of program execution and also other tasks. In a minute, I will focus on more or less profiling related features, because these features are very useful to find, obviously, timing issues and also bottlenecks in your application. Especially the call graph analysis is very useful, of which we will briefly take a closer look now. So the call graph analysis, or the call graph, shows the relationship between the executed functions. So which functions were called from a specific function, or vice versa, from which functions a specific function was called from. A call graph can be calculated from the recorded trace information. The ideal case is that the trace should cover the complete execution or the complete execution time of the interested part of your application. In the real world, it looks a bit different. In the real world, you will have to, in almost all the cases, only a limited time frame for which the trace data is available. So you have to select the time frame carefully. So this is caused by basically the available amount of trace memory you have either the on-chip trace memory on an AUX, for example, with up to 2 MB, or if you use a dedicated trace interface to get trace data off chip, the trace memory that is available in the access device. Together with the call graph, you will get also some statistical information like call counts and also additional information about the execution time. For detailed profiling information, the call graph window that UDE provides also contains a table-like view with more detailed profiling information, including the minimum, the maximum, and also the average execution times of the functions of your application, and those values are available for a inclusive measurement. That means also the execution times of the called functions are considered, and in the exclusive mode you only have the execution times of the functions itself without any called function that are executed. The call graph itself is presented in two ways. There is a static call graph and a dynamic call graph available in UDE. In the static call graph, the calls to a function are accumulated regardless of who was the caller. And in the dynamic call graph instead, it is also considered the caller. So you can see the difference in the example here shown on this slide. We have three functions here, A, B, and C. A is calling C 10 times, and then B is called 2 times, and also C is called by B. So in the static call graph, you only see the total number of calls here for C, 12. And in the dynamic call graph, we have differentiated between the caller of C. So if we call C directly from A, then we have 10 calls, a count of 10 calls here in the round bracket. And if we call C from B, then we have 2 calls, seen here in the round bracket. And in addition to the standard display of this call graph, we have for the dynamic call graph also a so-called timeline option. If this timeline option is enabled, every single call is presented in a separate node, not the calls are not accumulated anymore, and this will get you a maximum expanded tree, and we will see later how it looks like and for what it is useful. So with this and with these introductions, we are ready to turn finally to the promised example. For the demonstration, I use a tri-core or an AURIX TC39 from Infineon that provides us the MCDS on-chip trace. The trace data will be recorded on-chip in a dedicated trace memory. We have 2 MB available on that device, and the UDE, the debug tool, read this memory via the DEB interface, the debug interface that is provided by the AURIX device. So we do not need a trace memory on the debugger probe. So we can use the UAD2 Pro from our Universal Access device family for this, for our measurements. So the hardware setup looks like that. We have the UAD2 Pro connected using USB. You can see the USB connector here to my PC, and then we have the Infineon Aurix TC39 mounted on this triboard here. And we use the DAP interface. This is the DAP connector here on this board, and our JTAG DAP Infineon adapter to communicate or to access the target device and to read the trace data into the UDE software tool. What we need else is of course, a UDE running on the PC with the separate trace license, so that we can use or utilize the trace features of the Aurix. The application I use for the demo is not, of course, not the application that we have seen in the customer project. I cannot show you a real world application from a customer, but I have prepared a sample that imitates more or less the scene timing issues. The application realizes a simple cooperative scheduler on CoreOne. That scheduler executes tasks based on fixed time slots. There were a 10, a 50, a 100, and a 200 millisecond task. The timer for this scheduler is provided by CoreZero. That is not that important, but important is that the correct timing behavior is observed by a test function, and it issues an alarm by the safety management unit, by the SMU, whenever a task is executed or is not executed in the right time and the timing constraints are violated. You see here we have a critical path in this scheduling. Whenever all the tasks are scheduled in this way, then the overall execution time of all the 4 tasks must not exceed or must be below 10 milliseconds, so that the 10 millisecond task is executed the next time in its right time slot. What else? We have we have a variable called G_SMU alarm counter, which counts the alarms coming from the SMU whenever the timing constraints are violated. And we can also look in a task info structure for each task if there is a violation. So then this helps us to find out if there is any timing violation, and if there is any, which task was involved in that. And we have a periodical interrupt that is issued by the Capture Compare Unit 6 of the Aurix, which is also handled by CoreOne, and we will see what happens if this interrupt is issued. So let's jump to the UDE. For the demo, I would like to use the newest release, or the upcoming release of UDE, the UDE 2022, which will be released by end of April or first half of May this year, which provides us some new features and some nice new visualizations for trace-based measurements and other nice features as well. So I have prepared a workspace for that. A workspace is basically the debug session containing a ELF file or the target application that can be flashed to the target device. I don't want to flash it because I know it is already on my target. So I can verify if there is any changes happened. No, there's no changes. Everything is okay. And I have already opened some windows that I need to analyze my application. So you see, I have enabled only Core 0 and Core 1 of this RX device. There are 6 cores available, but for the demo, I don't need all of the 6 cores here, and so I save a lot of space on the screen here. So I start the application. And the first thing I'd like to show you, or I have to point you, is the watch window here, where we see the G_SMU alarm counter, and we see that it is counting up. That means that sometimes we have a violation in the timing constraints. So sometimes one of the 4 tasks are not executed right in time. And we can look into the provided task structure or task info structure. For each task, we have one entry here. This is for the 10 millisecond task. You can see it here on the period that is that we set up for this task, and we see that we have here a incrementing error counter. So it looks like that the task 10 millisecond is not executed periodically in all cases. So we have an error here. If you look at the other task, 50 millisecond, 100 millisecond, and also 200 millisecond, there are no errors here. So we can look at only at the 10 millisecond task, what happens. Okay. With this information, we have no idea what happens. So we need some more information, and we want to look into the runtime behavior using trace. So if you want to use trace, we have at first to define a so-called, we call it trace task, that will us allow to observe the execution of the tasks which are run on CoreOne. Best practice is that you start the trace at a specific point in time and to record everything after that. Or as an alternative way to trace everything between 2 points in time. For example, if you have a fixed period, then and you know, or you assume that within this period something is happening which should be happened, then you can trace also within 2 points in time. For this, I don't know much about the issue, so I decided, or we decided to use the first option to start the trace and trace from this point in time, and save as much as trace information as possible. In this hardware configuration, we have 2 megabyte trace memory available. To configure the trace, we are using a tool which we call UEC, which is the Universal Emulation Configurator, which is a tool that allows you to set up a trace task based on predefined building blocks. We have a library of building blocks here on the left side. These building blocks comes from a so-called compact library. Here, these are building blocks used for everyday tasks and for creating very fast and very simple trace configurations. There is also a advanced library available which allows you to define much more complex and flexible trace tasks for maybe some tricky trace-based debuggings. But for now, the compact library suits to us, and we can use some of these blocks for our trace task. The first thing we need to do is to tell the trace system how much trace memory we have available or we want to spend. We can change the setting up to 2 megabyte. The reason for providing this setting here is that the trace memory on the Infineon RX devices are also can be also used for calibration. So there may be a conflict between tracing and calibration, and the trace memory can be shared between these two use cases. So you can limit the trace memory here in the tool so that you can use in parallel also a calibration tool. But I have no calibration tool connected here, so I can use all the available trace memory. Then we need to specify a trigger. A trigger is like a pin needle in the trace memory, which is a kind of ring buffer. So once the trigger condition occurs, the trace is started in the pre-trigger case and stops automatically if the trace memory is filled completely, or if we want to use look back in time, then mostly the post-trigger mode is used. That means that you stop the trace recording on the trigger condition, and everything before the trigger condition is then available in the trace memory. But we want to start the trace at a certain point in time, and we want to trace CoreOne. Then we have to specify the trigger condition, which is basically a function in CoreOne, not sections, in functions, which is the CoreOne Worker. Looks like that. CoreOne Worker is executed periodically, and depending on the global milliseconds that we get here, it calls all the tasks based on the task information, the period information, and also a function pointer here. So I said at the beginning that we want to start the trace at a certain point in time and trace until the trace memory is completely filled. So I think that it's a good idea to start with the CoreOne Worker function. Then you can change the trace method here. Branch only means that you trace everything, every branch or every branch instruction in your functions, and this consumes a lot of trace, or may consume a lot of trace memory, and the RX provides us a alternative trace method called compact function trace, which only traces the calls and the returns in your function. That saves a lot of trace memory and expands the time that we have then afterwards for to analyze the application. We need some timing information, so we enable the so-called tick messages. Basically, these are the timestamps that we are using for the measurements and also for the visualization afterwards. Because we have some interrupts that may occur, the compact function trace are not aware of these interrupts, so we need some additional interrupt detection for the trace analysis. There is also a configuration block for that. Here we can also enable the timestamps, but we have timestamps globally enabled before, so we can leave it as it is. So that's all. With that configuration, we can now start trace. So the configuration is compiled. We can look into the trace memory in the trace window. The configuration is compiled now, and the configuration settings are downloaded to the target system, and we record some trace information. The trace is stopped automatically, and we see the compact function trace. Only calls and returns are traced, and in between there should be some information about interrupts. Yeah, here some interrupts. Okay, but with this, you can't do anything. It is a raw view that shows you nothing useful for investigating your timing issues. To investigate timing issues, we want to use the call graph analysis. The call graph analysis is also provided by a window which provides us the dynamic call graph, as mentioned before, static call graph, and so on. So also tables for profiling. I select the CoreOne for the analysis and start analysis. If the analysis has been finished, then we see in the dynamic call graph our CoreOne Worker, which called the tasks, and every task calls other functions. We see here an interrupt, for example, and also timings, total timings of all the functions, not timings by each execution of the functions. These are total timings. You have to, if you use the default setup for the call graph analysis, then you will not have the timings here in these labels. You have to add the timings to the label formatter using the right-click properties, and then in the second tab you can change the format of this label. I have added the total inclusive time for each function here in preparation of this webinar. Okay, but here we can't see any any issue. The issues are visible in the profiling information. So here all the functions are shown that are in the trace. And we can now sort the maximum time, and we will see some space, sorry, that if you look here, okay, CoreOne, that should be fine. The worker should also be fine. But if you look at the task 50 millisecond, it is on the third position here. If we sort any maximum time, execution time, there are obviously some of the executions of task 50 millisecond which took 21 millisecond. And if you remember on this slide before, where I showed the principle of the application, then I said the worst case execution time of all the tasks must not be exceed 10 milliseconds. So here there is something wrong, and we want to see what is wrong with that. For that, we change the dynamic call graph to the already mentioned timeline mode. And if we start the analysis again, why it's not? Okay. If we look at the dynamic profiling, looks a bit different. We see for every executions a single node for the executed functions, and if we sort by the total time, then we see here 5 executions of the 50 millisecond task, which took too long. And right-click Show in Graph navigates us to the specific execution in this timeline mode, which shows us, okay, there is something wrong with that. We see, okay, the task 50 milliseconds took 21 milliseconds. We call the check-in time from a function from there, but we also be interrupted by the CCU6 timer interrupt. And this took too long, 16.6 milliseconds. There's a long delay function called, which may be, or which is the culprit for our timing issue that we have seen here by the SMU alarm counter here. If I go to, for example, can switch to the functions here, we can look into the functions and we see, okay, this is a bit artificial here. I check if the timer 50 millisecond active, and then I delay it. And this is a very stupid bit of code for this example here. The real application from our customer looked a bit different here. They do not such stupid things. They had a nested interrupt which took too long, but with this tooling they found out the reason for their violated timing constraints. There's another few which may help you to find timing issues, which is the so-called execution sequence chart, which provides us a timeline view to all the executed instructions over the time. You're on the x-axis, this is the time, and here we see all the executed functions, and you can zoom in and see, okay, maybe, where is it? If we zoom in, that we see our 10 millisecond task here executed periodically. Looks quite good. Can measure the time, 10 milliseconds, it's okay. And here we see our issue. So the 50 millisecond task is interrupted here by this interrupt, which calls the handler, and the handler itself calls this delay function here. And you see we need, can measure that timing, we need 21 milliseconds to execute the 50 millisecond task. And while this execution, the 10 millisecond task had no chance to be executed right in time. Okay, that ends the last webinar in our series of webinars. I hope you found it interesting and useful. If you have any questions, then please use the webinar panel as introduced by Wolfgang at the beginning. We will collect these questions and answer them by email after the webinar. All the webinars are recorded, and the recordings will be available soon at the Hitex Germany YouTube channel, and also we will have links at the PLS homepage for that. Thank you very much.